So we are discussing the topic D and F block elements, right? So we have started with the general properties of transition elements. So we were discussing this concept, right? So these are the things which we have gone through. Okay, general properties of transition metals, that is metallic character, right, reducing power, density, melting point, boiling point. So then we had seen the general properties like the electronic configuration. Okay, electronic configuration. Then we have discussed about the ionization enthalpy, oxidation state, then magnetic property, right, and then formation of colored ions, right. So today we are going to discuss about formation of complex compounds. Okay, so the remaining properties we are going to discuss. So let us discuss. Okay. So we are going to discuss about formation of complex ions. Okay. So most of this, so formation of complex compounds. Okay. So here, so this transition metals, okay, they have the tendency to combine with ions or neutral molecules, okay, and they form complexes. So how this, what do you mean by a complex? Okay, so when they link, okay, metals, when they combine or when they link with the ions, okay, with the ions or negatively charged, that is ions are nothing but your negatively charged, or the neutral molecules, they are said to be ligands, okay, and what they form is they form a complex. So we are going to discuss the complex compounds, okay, in a separate topic, that is coordination compounds, so that we are going to discuss. So here metal will be in the center and the ligands will be linked, okay, to the metal, and thus what they form the complexes. Okay, they form what complexes? For example, okay, for example, FeCN6 3 minus. You can see here FeCN6 3 minus. So how it will be? So Fe is a metal and it is linked to 4 Cn minus. Okay, it is linked to 4 Cn minus. Okay, ions, and sorry, 6. It is 6, right? So okay, I didn't see. Oh, let me write here. So Fe, so 1, 2, 3, 4, 5, and 6. So it is Cn minus, Cn minus, Cn minus, Cn minus, Cn, Cn. So Fe, Cn6, and 3 minus. So like this are the complex compounds. So these transition metals, they will combine with the ions or the neutral molecules, and they form what? They form the complex compound. So these are the examples like FeCN6 3 minus, then FeCN6 4 minus, okay, then CuNH3 6 3 plus, okay, cobalt, that is CuNH3 6 3 plus, then platinum Cl4 2 minus. Okay, so these are some of the complex compounds. So these are the examples of the complex compound. Okay. Now, so this why is this tendency of the metal ions to combine with this different ions? Okay. So this is due to, okay, two main reasons. First is the transition metals, they have a very small size. Okay, they have a very small size and they have very high positive ionic charge. So the charge on the metals, that is the transition metals, it is very high. Okay, and thus what will happen? Okay, to the charge density is also quite high. So how do you calculate the charge density? So charge density is equals to charge of the ion upon the size of the ion. So if the charge is more, obviously the charge density will be more. So this is the first point, that what is the why the transition metals they form complex compound. The reason is that because of the small size, because of their small size and high ionic charges, okay, they have that ability to combine with the d orbital, so that bond formation is possible. Okay, so this is the first reason. So transition metals, what is the reason? They have a very small size and high ionic charges, and because of that they have high ability of combining the d orbitals to form bond. Okay, so bond formation is possible. So this is the first reason. Now second reason is what? This makes the acceptance of electron pairs from ligand easily. So the ligands can accept the pair of electrons easily. Okay, because of this reason. Then second is that these metal ions will have empty d orbitals. Okay, they will be empty d orbitals. Okay, with the proper energy, so that they can accept pair of electrons from this ligand. So ligands, what are the role of ligands? Yes, so ligands, or suppose ligands like your Cl minus, F minus, okay, Cn minus, then neutral molecules like water, NH3. So these are all ligands. So what ability they have? They have the ability to donate a pair of electrons to the metal. Okay, and they combine to give you a complex compound. So now when we are discussing about the ligand, so these ligands, these metals, they are having empty d orbital, okay, with a appropriate energy. Okay, what it can do? So that it can take a pair of electrons from this ligand. So ligands are what? Ligands are they give a pair of electron. Okay, so they donate pair of electron to the metal and they combine to form the complexes. So these are the main 2 points, okay, of formation of this complex compounds. Okay, then so the ions, so whenever the ions are having higher oxidation state, so if the ions are having higher oxidation state, that means they are more stable. Okay, so ions with higher oxidation state are more stable complexes than with the lower oxidation state. So whenever the oxidation state is higher, that means they are highly stable as compared to that of the ions with lower oxidation state. Okay, now suppose I give you example like K3 Fe Cn6, okay, and K4 Fe Cn6. Now what you can tell me here? Yes, which is more stable? So these are the two complexes. So which can be more stable here? So here,
K4.
what is the charge over here? So the charge is plus, okay. So because we are adding K3, okay, so the charge on the complex, so this is +3, okay. And here, okay, so here what is the charge? The charge will be +4, okay. Now here, K3 ion, it is more stable. Why it is more stable than this? Because you can, that is K4 ion is more stable than that of the K3, right? Why? Because it is in higher oxidation state. It is having higher oxidation state. So K4, okay, so this complex is more stable as compared to this complex. Okay, so this is the first point. Then the stability of complex. What happens to stability of complexes? It increases with the increase in atomic number. Okay, so for example, so complexes of copper +2 ion are more stable as compared to that of Mn+2, because the atomic number of copper is 29 and that of manganese is 24. Okay, so 25. Okay, so like this, uh, uh, so as the atomic number increases, the what is that? Stability of complexes also increases. So another point for formation of complex compounds. So this is about complex formation of complex compounds. So what things you have to remember? That transition metals, okay, so they form the complex. Okay, the possibility is that it is due to the smaller size of the metal ions, okay, and high ionic charges, and because of the availability of d orbitals, they can form the bond formation. Okay, so that the ligands, they can accept the pair of electrons from the ligands. Okay, and the metal, center metal of the d orbital, that is for transition metals, they are empty. so that whatever the ligands are donating the pair of electron, they can accept it. Okay, and thus it forms a stable complex ion. So ions, whenever they are having higher positive oxidation state, so they are more stable as compared to the metals with lower oxidation state. Okay, and the stability of complexes, what will happen? Stability as the atomic number increases. Okay, as the atomic number increases, the stability of the complex also increases. So these are some of the points for formation of complex compound. Next is what? Catalytic property. Okay, catalytic property. So what is the catalytic property here? So most of the transition metals are used as catalyst. Now we know what is the role of catalyst. Okay, so what does catalyst do? So catalyst, it will what it will do? It will increase the rate of reaction. Okay, by without any alteration in the equilibrium. Right. So catalyst, it is used in speeding up the rate of reaction. So most of the transition metals, they are used as a catalyst. Why? What is the reason? Because of the presence of incomplete or empty d orbital. Because most of the transition metals, they are having empty or completely or incomplete or empty d orbitals. The d orbitals are either incomplete or they are empty. So this is the first reason. Second is that they are having large surface area. Okay, they are having what? They are having large surface area. Third is it will show variable oxidation state. Now you know what I mean by variable oxidation state. Variable oxidation state means what? They will show different oxidation states. Okay. Then ability to form complexes. So catalytic properties. Okay. Why it is used as a catalyst, the transition metals, because they have the ability to form complexes. So which are the metals which are used as a catalyst? So Fe, okay, nickel, okay, then vanadium oxide. So this is another complex. Then platinum, okay, molybdenum and cobalt. Okay, so these are some of the metals which are used as the catalyst. So most of the transition metals, they are used as the catalyst. Okay, so these are the different this. So we know that where Fe is used. So Fe we have seen where Fe is used. So Fe is used in the, it acts as a catalyst in Haber's process, right? In Haber's process, Fe, like ferric oxide, it is in the form of ferric oxide. So ferric oxide, it acts as a catalyst in Haber's process. Then your nickel. So where nickel is used, so nickel, it is used as a catalyst in hydrogenation of oils. Okay, in the hydrogenation process of oil, there we use nickel as a catalyst. Then your vanadium oxide. Okay, so this is acting as a catalyst in a process which is called as contact process. So contact process is a process where we are manufacturing the sulfuric acid. We are manufacturing which acid? Sulfuric acid. So for the manufacture, we are using the vanadium oxide. Okay. So compound of vanadium oxide. So these are some of the examples, okay, of the catalyst. So why the transition metals, they have this property of catalytic property? So the reasons are because of incomplete or empty d orbitals, large surface area, variable oxidation state, and availability of ability to form complexes. Okay, so this is the second, okay, second properties of transition metals. I hope it is clear. Yes. So formation of complex compounds, and we have seen catalytic properties. Then, so catalytic properties important. So please mark important as for 2 marks. Okay. So it can be a question asked for 2 marks. Explain the catalytic property of transition metals. So you have to explain. So why the most of the transition metals are used as catalyst? Okay, what is the reason? And then you have to give some of the examples of catalyst and where they are used as a catalyst. So you can give the examples of Fe, nickel, vanadium oxide. Okay, so these are some of the examples, okay, of catalyst. Next, we are going to see is the formation of interstitial compounds. Another question important for 2 marks. Okay, so there can be a question. Explain why transition elements are are involved, or how they form interstitial compounds. Okay, how transition metals form interstitial compounds. So this can be a question for 2 marks. So how will you explain? Now, what do you mean by interstitial compound? Okay, so interstitial compounds means what? Okay, now whenever you have any crystal lattice, okay, whenever you have a larger crystal lattice, suppose we have a crystal lattice of sodium chloride. So sodium, okay, so you know that chlorine, we know that negative ions, that is anion, are always larger than that of the cation. So chlorine atoms, okay, Cl, then Cl, Cl, like this. Okay, now in bit, or you can write it like this. Just a second. So Cl, then comes your Na plus, then Cl, then Na plus Cl. Okay, then this, like this. So what you can see, so this is a crystal lattice of NaCl. So Na will be what? Na will be having a smaller size because cations are always smaller as compared to that of the anions, and anions will have a larger size. Okay. Now when we are comparing the anions and cations, so this is a crystal lattice like this. Now suppose, now what are this interstitial compound? Now you can see that there is some gaps, right? You can see some gaps, or they are called as voids. They are called as what? Voids. Okay, voids means the small gaps. Okay, the small gaps between the big crystal lattice. So that is called as a void. Okay, void, or the space. Okay, small space. So this interstitial compounds are those which are formed when small atoms. So in this small spaces, some atoms, small atoms, okay, like your hydrogen, carbon, nitrogen, okay, they go and fit there, okay, they go and take their place. So such what compounds, okay, such compounds where these small atoms like hydrogen, your carbon, nitrogen, okay, they get trapped inside the crystal lattice of these metals. They are called as interstitial compounds. What they are called as? Interstitial compounds. So what do you mean by interstitial compound? Interstitial compounds, okay, so these are those which are found when small atoms like hydrogen, carbon, or nitrogen are getting trapped inside the crystal lattice of metals. Okay, so this is the meaning of interstitial compound. So these transition metals, they have voids or interstitials in which the carbon, hydrogen, nitrogen, boron will go and fit in that. Okay, so thus it results into what? It results into interstitial compound. Now these are non-psychometric in nature. What do you mean by non-psychometric? Non-psychometric means the ratio or the composition. Okay, the composition is not fixed. It is not fixed. Why the composition is not fixed? Because it is non-psychometric. Non-psychometric means their composition is not fixed. For example, steel. Okay, for example, steel. And these interstitial compounds, they are hard and they are less malleable and ductile. Now, other examples of interstitial compounds like titanium carbide, okay, Mn4n, then Fe3H, okay, then VH. So here the crystal lattices of vanadium and hydrogen is present in 0.5. So the concentration, okay, it is you can see the composition is very this, okay, it is not proper. So it is 1.7. You can see here. So these are the examples of what? Interstitial compound. So interstitial compound means in between the interspaces, the small atoms will go and occupy their space. Okay, and such a compounds, okay, which are found are called as interstitial compounds. So these interstitial compounds, they are formed by what? Transition metals. Okay, so most of the transition metals, they form this interstitial compound. So they have another unique property to form the interstitial compounds. Okay, then so what are the different physical and chemical properties? Okay, so what are the different physical and chemical properties of these compounds? So these are having large, high melting point and boiling point. Okay, as that of the pure metals. Then they are very hard. Okay, they are very hard. Then they are having metallic conductivity. They are chemically inert. Okay, and they are non-psychometric in nature. Non-psychometric means what? Their composition. You can see that their composition is not uniform. Okay. Then, so this were the points. These are the properties of transition metals. Then the last property of transition metal is alloy formation. Okay, so these alloys, they are homogeneous solid solution in which atoms of one metals are distributed randomly among the atoms of the another. What do you mean by alloy? Alloy means it is a homogeneous mixture. Homogeneous mixture means what? When two or more components are added, okay, so they form a mixture. Homogeneous mixture means there won't be any boundary. Okay, there won't be any so there will be a uniformity. Okay, there will be no boundary between this composition. So this alloy, it is a heterogeneous mixture of two or more metals. Okay, because of the comparable size, because these transition metals, they are having almost same size. Okay, so one metal, it can be displayed by the another metal in the crystal lattice, and thus we can form the what we can form? We can form the alloys. Okay, these alloys are very hard and they have high melting point. So alloys are formed when the metals are having similar radii. Okay, so alloys are formed by the atoms with the similar metallic radii. So between the similar atoms the of same radii, okay, the alloys are formed. So alloys are nothing but they are the homogeneous mixture in which one metal is combined with another or two or more metals. Okay, now transition metals, they have that tendency. Okay, so these transition metals, they are used in the alloy formation. And this it is so what are the characteristics? For example, in steel, okay, in stainless steel, so what all are used in stainless steel? Yes, in stainless steel, your ferrous alloys. Okay, in that chromium, palladium, okay, then molybdenum and manganese are used for the production of a variety of stainless steels. Okay, then for brass, so alloys, so the example of alloy can be your brass also. So in brass formation, so two elements like your copper as well as zinc. Okay, so transition metals can form alloy with non-transition metals also. Then bronze is another example where copper and tin. Okay, copper and tin gets okay, they are having a homogeneous mixture to form the alloy. Is it clear? Yes. So these are some of the important properties, okay, general properties of your D block elements. Is it clear? So we have seen the different general properties, okay, electronic configuration. Then we had discussed about what electronic configuration. Then we have discussed about the ionization enthalpy, then oxidation state, okay, then magnetic property, okay, then we have seen how to calculate the magnetic moment also. Then we have discussed about the formation of colored ions, then formation of complex ions, complex compounds, then what is the catalytic property, okay, then formation of interstitial compounds, right, and then the alloy formation. So these are some of the important properties of your D block element. Is it clear up to here? Any doubts? Yes. Up to here, is it clear? So then we are going to discuss about the important compounds of D block elements. So there are some of the important compounds, okay, of D block elements, so that we are going to discuss. Okay. So any doubts up to here? Okay, fine. So let us continue. So next we are going to see some of the important compounds of D block elements. So very important. Okay, so we are going to discuss two important compounds, that is potassium permanganate and potassium dichromate. So very important for 3 marks. So please make a note. So very important for 3 marks. So they'll ask you the preparation of either potassium dichromate or potassium permanganate. Okay. So how the preparation takes place? Marks. Okay. So these are some of the important compounds of transition elements. So the two main important compounds we are going to discuss. So based on that, you are going to get the. So one is a sure question. Okay. One anyone is a sure question. So first we are going to see is potassium dichromate. So how is potassium dichromate given? Yes, it is K2Cr2O7. Okay, potassium dichromate is K2Cr2O7. That is, the ore which is present is a ferrochrome or chromate ore. So please, 1 mark question, very important. Which is the ore used for the preparation of potassium dichromate? So what is the ore and the composition? Very important. So mark this as important. Please make this a note in your book. Okay. So which is the ore? It is a ferrochrome or chromate ore. And please see the composition also. FeO.Cr2O3 or FeCr2O4. Okay. So this is the ore. Now what we are doing here? We are manufacturing. Okay, we are preparing. What do you mean by manufacturing? Manufacturing means we are doing the preparation. Okay, we are going to prepare the potassium dichromate from the chromite ore. We are going to prepare it from a chromite ore, that is FeCr2O4 or FeOCr2O3. So we are going to prepare it from the chromite ore. Okay. Then the first step is what we are going to do. See here, the first step is here. Okay. First step is that the chromite ore, whatever the chromite ore we are going to take. So this chromite ore, we are going to fuse it with sodium chloride. Fuse means nothing but we are going to react. Okay, we are going to react the chromite ore with sodium chromate. I hope you are writing down the steps. Okay, very important. So, chromite ore, it is fused with the chromite ore with the sodium chloride. Okay, or you can take sodium chloride or potassium chloride. Sodium chloride is Na2CO3, potassium chloride is K2Cr2, K2CO3. Okay, so either you can take sodium chloride, or you can take what? Potassium, sodium carbonate, or you can take potassium carbonate. Okay, in the presence of excess of air, Okay, and what is the reaction, just see. So potassium, your bromide ore reacts with sodium carbonate, okay, in the presence of excess of air to give you sodium chromate. What you get the product as? Sodium chromate. So if you take your sodium carbonate, you will get sodium chromate. If you take potassium carbonate, you will get potassium chromate. Okay. So depending upon which base you are going to take. So if you take sodium carbonate, you are going to get sodium chromate. If you are going to take potassium carbonate, then you'll get potassium chromate here. Okay. Plus 8 this what carbon dioxide. Okay. Whatever the color or whatever the reaction takes place, so the color of this reaction is yellow in color. Okay, you get a yellow color reaction. Okay. Now to this yellow color solution of sodium chromate, the yellow color solution, it is due to the color due to the sodium chromate. So the color, that is the yellow color sodium chromate solution, what we are going to do? We are going to filter it. Okay, we are going to filter it using filter paper, and we are going, whatever the filtrate we obtain, to that we are going to add the acid. Okay, which acid? We can add any acid. So here I am going to add what? Sulfuric acid. What we are going to add? We are going to add sulfuric acid. Okay, we are going to add sulfuric acid to the yellow color filtered solution. So what we are doing? We are going to acidify the solution. Okay, acidify means what? We are going to add acid to the solution, right? So we are going to acidify the solution. And what we get? We get sodium dichromate. What we get is sodium dichromate. Na2Cr2O7. Here Na2Cr O4 is sodium chromate, and what is sodium dichromate is Na2Cr2O7. Okay. Plus plus 2Na plus. Okay, plus 2Na plus and H2O. This color solution is orange in color. Okay, the color of the solution turned will be orangish color. Okay, because you are converting your sodium chromate to sodium dichromate. Okay, why? After acidifying the solution. So after acidification, we get what we are going to do. In the third step, the solution of the sodium dichromate, we are going to treat it with potassium chloride. We are going to treat it with what? Potassium chloride. And what we are going to get? We are going to get it as potassium dichromate. What we are going to take? Potassium dichromate. Okay. And these, so potassium dichromate, what we are going to do? We are going to cool this solution. Okay. After cooling the solution, the orange crystal, it will convert into orange crystals. Okay, so this orange crystals, it can be separated out. It can be separated out. So on cooling, whatever the orange crystals you get of potassium dichromate, it will get separated. So these are the 3 steps. These are the 3 steps for the preparation of potassium dichromate. First step is what? We are going to take which ore? We are going to take for manufacturing of potassium dichromate. We are going to take your chromite ore or your ferrochrome. Okay, FeOCr2O3 or FeCr2O4. So what we are going to do in the first step, we are going to take the chromite ore, we are going to fuse or we are going to react it with sodium carbonate. Okay, in the presence of excess of air. What we are going to get? We are going to get sodium chromate O plus. Okay, Fe2O3 plus 8H carbon dioxide. Okay, so whatever the color of the solution obtained will be yellow in color. Now for this yellow color solution, what we are going to do? We are going to filter it. After filtration, I am going to add acid to that. We are going to do acidification, and the chromate ore are converted into dichromate. Okay, and the resulted solution is orange in color. Now this orange color solution, to this what I'm going to add? I'm going to add potassium chloride solution. Okay, potassium chloride, and the sodium dichromate are converted into potassium dichromate and NaCl. Then on cooling, whatever the solution is there, it is converted into its crystals of your potassium dichromate. So these are some of the so these are the points, okay, of potassium preparation of potassium dichromate. So whatever the sodium dichromate is there, so it is more soluble. Okay, it is more soluble it is more soluble than your potassium dichromate, whatever the sodium dichromate is there. Chromates and dichromates, they are interconvertible in aqueous solution depending upon the pH of the solution. So whatever we are converting the chromates into dichromates, okay, and then we are converting the sodium dichromate into potassium dichromate. So they are interconvertible. They can be converted from one form to another. Understood? Is it clear? So very important. So as I've said you, it is a very, very important question asked for 3 marks, compulsory asked question. So please make so please write it down. So whatever the steps are there, okay, it will help you. So whatever important points you feel, please make it a note. Okay, so let us go for the next one. Next is potassium permanganate. So the second, no, before that, okay, before that, the properties, we did not discuss the properties of potassium dichromate. Okay, so this potassium dichromate, where it is used as a primary standard. Okay, it is used as a primary standard in volumetric analysis. Okay, in volumetric analysis. Now for analysis, so as it is having a dark color, okay, that is orange color. Because of that, it is used as a primary standard. Okay, against different solutions, okay, in the volumetric analysis. Volumetric means what? We are going to determine the quantity, how much salt is added to give you a given concentration. Okay, so this is the first property. Then second property is what? So in acidic medium, okay, this potassium dichromate, it is acting as a strong oxidizing agent. It acts as what? It acts as strong oxidizing agent. Okay, so this is the second point. Then third point is that, so when we are converting, okay, so interconversion of chromate to dichromate can be done easily. So it is observed that in acidic medium, chromate ore can be converted into dichromate, and in basic medium, chromate ore can be converted into dichromate, can be converted into chromate. Okay, so these are the what? So this, whatever the interconversion is there, it will depend on what? It depends on the pH of the solution. Okay, so let us see the structure, very important. So this is very important, mark this as important. So the structure of chromate ion. Okay, so it is having a tetrahedral structure. So Cr, O, 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 and 2 minus. Okay, now dichromate, let me draw here. Dichromate. Okay, so this is a dichromate ion. Okay. Fine. So please draw the structures. Very important. It can be asked. Draw the structure of chromate ore and draw the structure of dichromate ore like this. Okay. Fine. So let us go for the next one. Potassium permanganate. Okay. Next is what? Potassium permanganate. So how is the preparation of potassium permanganate? It is prepared by fusion. Okay, we can fuse, we can react our MnO2, that is pyrolusite. It is what? Pyrolusite. Okay. So which is the ore from which KMnO4 can be prepared is pyrolusite. Okay, that is MnO2. So what we are doing, we are going to react the MnO2 with KOH with potassium hydroxide. Okay. So your MnO2, that is pyrolusite, it is reacted with potassium hydroxide, or you can take NaOH, or you can take what? Sodium hydroxide. Okay. So pyrolusite, it can be reacted with either potassium hydroxide or your sodium hydroxide. Okay. And you can use any oxidizing agent, like we can use, we are using here air itself. Okay, we are using excess of air for oxidation purpose, or you can use potassium nitrate solution. Okay, then what it will give? It will give you K2MnO4. What you can give? K2MnO4, and this is a green color solution. The solution color will be green in color. So what we are going to do? We are going to take pyrolusite. We are going to react it with the base like sodium hydroxide or potassium hydroxide, and we are going to use a oxidizing agent like your potassium nitrate or air. Okay, excess of air, we are going to get what? We are going to add green color solution, which is a K2MnO4. Okay, and this K2 now this whatever K2MnO4 is there, that will get disproportion. Disproportion means what? It will get splitted. It will get bifurcated. It will get splitted into different products in the acidic medium. So we are going to apply acidic medium, and in the acidic medium, what we are going to get? We are going to get potassium permanganate, MnO2, and water. Okay, so these are the reactions of pyrolusite. So that is reaction of KMnO4. Commercially, how you can prepare commercially? So pyrolusite, if you fused it with KOH, okay, or when you oxidize it with the air, you get manganate ion. This manganate ion, if you do electrolytic oxidation, if you provide electrolytic oxidation, it is converted into permanganate ion. So this is a green color solution, and this is converted into purple color solution. So due to the purple color, it is also acting as a standard solution. So we use KMnO4 as a standard solution. Potassium dichromate, the color is orange color, and potassium permanganate, the color is what? It is purple color. Okay. So these are the reactions of your KMnO4. Can you tell me, now I have a question. Can you tell me the oxidation state of Mn here, and oxidation state of Mn here, Mn here, and here? Can you tell me the oxidation state in all the cases? Yes. Can you tell me the oxidation states? Do you know how to calculate? Okay. Pavitra has answered it as +2. +2 for which? Yes, +2 for what?
For Mn, ma'am.
No, which Mn? MnO2, Mn.
MnO2, ma'am. 2
Okay,
MnO2.
Okay, don't consider it 2. 2 is a psychometric ratio. Okay, we'll consider only MnO2. So
Next,
MnO2.
K2 MnO4 is +4, ma'am.
Okay. This you told +2. And then
Next, MnO4 2 minus is +4, ma'am.
okay. And these
+4, ma'am.
and MnO2
+2.
Okay, let me see. Okay, fine. I'll tell you. So MnO2, okay, MnO2. So we have to find for Mn. So keep it as X plus oxygens. How many oxygens are there? 2. Each oxygen, what is the charge of each oxygen? Can anyone tell me what is the charge of each oxygen? What will be the charge on oxygen?
-2.
Yes, very good. -2. Okay, so the whole charge on this is what? 0. So we keep it as 0. So now solve this. X is equals to -4 equals to 0. So if you transfer there, it will be x is equals to +4. So the charge is +4. Okay. So the charge is what? +4. Okay. Now similarly, now you can apply for this K2MnO4. K2MnO4. K. Can you tell me the charge on K?
No.
Yes. Can anyone tell me the charge on K? Potassium. Potassium is a
Which
alkali.
K, ma'am? Potassium hydroxide, ma'am.
Potassium.
For which K, ma'am? Potassium hydroxide.
Commonly, what is the oxidation state of K?
0.
K? No.
1.
It is plus. Yes, it is a +1. Okay. See, where potassium comes under alkali metals. Okay. Alkali metals, what is the oxidation state? Okay, the common oxidation state shown by potassium is +1. So it is +1. So how many of potassiums are there? 2. So we will write 2 into 1 plus. We are finding Mn. So we'll keep it as X plus. How many oxygens are there? 4. Then each oxygen, what is the charge? -2. Then it will be 0. Can you solve this? So 2 plus x minus 4 to the 8 is equals to 0. Then x is equals to -6 is equals to 0. So it will be x is equals to 6. So the charge is +6. Okay. Now the next one, MnO4 -2. Again, we are finding out for Mn. So keep it as x plus 4 into -2, because each oxygen is -2, is equals to the charge on the complex is -2. Okay, if there is no charge above, then it will be 0. But here there is a charge, so it is -2. So after solving this, x is equals to -8 is equals to -2 x, then -2 plus 8. So it is x is equals to 6. So the charge is what? +6. So here it is +6. Okay. Now MnO4 minus. Now take for MnO4 minus. Mn is x plus 4 into -2 equals to -1. So x 4 to the -8 is equals to -1. X equals to -1. This +8. So it is x is equals to 7. Understood?
Yes, ma'am.
Yes. So like this. So what are the charges? So this is +4. This is +6. This is +6. This is +4 and plus. This is also +4. Okay. So like this. No, I did not find it for this. No. Or I did. This is MnO4. MnO4. So what is happening? So you can see how Mn is undergoing different oxidation state. So Mn is showing +4, +6, +7. Right. So these are the different oxidation states shown by Mn. So this is the preparation of KMnO4. Okay. So KMnO4, what is the property of KMnO4? It is a good or it is a strong oxidizing agent. It is a strong oxidizing agent. Okay. So agent in several reactions. Right. Then what are the different properties? KMnO4, okay, it is a strong oxidizing agent. And what color it is having? It is having a purple color. Okay, it acts as a standard, what do you say? It is used as a primary standard. Okay, it is also used as a primary standard for different polymetric reactions. Then Why the purple color? Why most of the, as we have said, okay, I've mentioned you before that transition metals, they form colored complexes, right? So here only we can see the two best example. Now one is the metal, that is Mn. Okay, so it is a potassium permanganate, and another was K2Cr2O7. So chromium complex. So this was what color? Orange color, and this is purple color, right? So as we have mentioned that the transition metals, they are colored complexes. Can you tell me what was they form colored complexes? Why they are showing so intense color, dark color? Yes, what is the reason? We have discussed this in colored. They have the tendency to form colored complexes, compounds, transition metals.
It is a chemical compound.
No. Why transition metals, they form colored complexes? We have discussed this in the properties. Why transition metals are showing this colored complexes? Why they are showing? You can see now only, right? We have discussed just now. Potassium permanganate, it is purple color. Potassium dichromate, it is orange color. Okay, it is see here. If I want to show you where we have discussed. Okay, so it has that unique property of forming the colored complex. Okay. Yes, due to unpaired electrons. Okay, due to the presence of unpaired electrons. Due to the presence of unpaired electrons, most of the most of your transition metals, they are what they are exhibiting this property of, they form color complexes. Okay, so they undergo DD transition. So from lower energy to higher energy, they will absorb the radiation from the visible region, and when they go into the higher excited state, they have to come back to the lower excited state. That time they will emit the radiation complementary, and that complementary color will be would be seen in what, in this transition metal complexes. Okay, so these are some of the reasons. And suppose, okay, if you have unpaired electron, now you know what do you mean by unpaired electron. Okay, when there is a paramagnetic behavior shown by the complex, that is when you have unpaired electrons, okay, in that system, then they'll exhibit color property. If you have D0 and D10 system, then what is the property? Yes, it will be colorless. Very good. So it will be colorless. So whenever you have D0 or D10 system, it will be colorless. Then other than then, okay, they will be colored complexes. Okay. So these were the properties which we have discussed. So these all things you have to apply. Okay, very important. So these are the points. So they act as a strong oxidizing agent. In presence of dilute sulfuric acid, KMnO4 is reduced to manganese salt. You can see. So from MnO4 minus. MnO4 minus is what? +7. We have seen just now. So from +7, in the presence of acid, it is reduced to +2. Reduced means what? There is a, you can see, decrease in oxidation number. Okay, decrease in oxidation state or oxidation number, it is said to be a reduction. Okay, so from +7 to +2. So in the presence of sulfuric acid, it is getting reduced to manganese salt. Okay, this acidic sulfuric, that is KMnO4, what it will do, it will oxidize the oxalate to carbon dioxide, iron and iron 3, nitrates to nitrates, nitrites to nitrates, and iodides to iodine. So these are the reactants. Okay, so KMnO4, why it is acting as an oxidizing agent? Because these are the different reactions. Okay, wherein you can see how it is getting oxidized. So oxalate ion is getting oxidized to your this what, carbon dioxide, Fe+2 to Fe+3, NO2 minus, that is nitrite to nitrate ion, then iodide to iodine. Okay, so these are the different properties of your KMnO4. Is it clear up to here? Okay, is it clear? Now similarly, okay, similarly, homework for you all. Find the oxidation state of this Na2CrO4. Okay, then Na2Cr2O7 and K2Cr2O7. So you have to find the oxidation state of chromium. Okay, chromium, Cr, only Cr, not Cr2. So find the oxidation state of chromium in this. So I want the this. Okay, you have time still? No. Okay, fine. So you can take this as homework. Okay, sodium chromate, sodium dichromate, and potassium dichromate. So take this as homework. So in the next class, I'll be asking you the oxidation state of this. So we have completed the important compounds of transition elements. Okay. So next class, we are so we have left with the structures. Okay, remember. So in the next class, I'll tell you the structures of manganate ion and permanganate ion. So that we'll also discuss. And after that, we are going to start with F block elements. So this completes your D block elements. In the next class, on Monday, okay, on the Monday, we are going to discuss F block elements. Is it clear? So please go through the things, whatever have been told about D block elements. So if you have any doubts, you can ask me, okay, on Monday. Fine. So anything you need to ask me? Yes, any doubts?
No, ma'am.
Okay. Fine. I hope others are also having no doubts. Fine. So I shall end the session. So if you have any doubts, so please go to the things, whatever have been told about the block elements. Okay. So a small part is there. I'll just be telling the structures and we'll see the oxidation state of these. And then we are going to start with the F block elements. Fine. So thank you. Okay. Have a good weekend. So please study whatever have been told and come back on Monday. Okay.